Well, welcome to another video, and in this one we're going to be looking at sequential logic. And unlike combinational logic, which we looked at in the last video, sequential logic is not concerned only with the current state of its inputs, but also with the state that it's in at the moment. So, it has a memory or a feedback of some kind. And we'll start by looking at the most basic thing, the SR latch, and develop on from there. Starting at the beginning then, what we've got here is the set reset latch, and this is really the most basic kind of flip-flop we have. And as you can see, what we've got is we've got two pull-down resistors there, and they're keeping these two pins on the integrated circuit reliably low, and we have outputs. And if I do this, I set the simulator running, and if I do this, and then this, and this again, and if I keep on doing this, and you'll see it doesn't make a blind bit of difference to the output. It still stays on the set output. And again, and there we are. And that sort of thing you'd see in industrial machines. You could probably have a solenoid pushing those if you want to automate it. And you can have the Q output and bar Q output active, and in electronics we use that sort of thing all the time for if we want a machine to do two different processes on a single input, like this. And moving along, the idea of the set reset latch is illustrated here. And what we want you to notice is that, again, there's a low level and there's a high level. If I do this, and the idea is illustrated here, and that it's two not AND gates, and basically what we do is we feed back the output from one to the other in both cases. We keep it high this time and send it low through the switch, and again that's an industrial application, and you could probably put a read relay on there to switch over. But the point is there's a low level and there's a high level. If we move on a little bit more, here it is in its basic format, and you can see the feedbacks there, and you can also see the problem. Okay, so what I'd have to do is, if I kept the reset switch high and set that low, it'll switch over. If I now keep the reset switch high and set that back to high, it won't do anything. If I keep the set switch high and set the reset switch low, it'll go over. But as we saw, if we've got both on low, both outputs are active. Now again, in electronics we can deal with that, we can actually use that, but in data handling it's no good. You can't tell whether that's supposed to be a 0 or a 1. And in computer sciences this is considered illegal. So engineers looked at this and they came up with all sorts of things, and the JK flip-flop was invented, and another solution was to do this, and that's put an inverter in between, and what you can do then is like that, like that, like that, and so on and so forth. The problem with that is every time the pulse changes, so does the output. And that might not be what you want. Or then again, it might in the electronics, we can use that too. So, adding more NAND gates in gives you a D-type flip-flop. And as you'll see, we've got a clock on a D-type flip-flop. Now, that's important because that makes it synchronous. All the ones we've seen so far have been switched without the use of a clock pulse. This one is switched with the use of a clock pulse. So, as you can see at the moment, the set is active. So that would be Q. If I wait for the clock pulse to go low again, and I switch over, nothing happens until the clock pulse goes high. And again, if I wait for the clock pulse to go low and I switch over, nothing happens until the clock pulse goes high. And that's quite important. Now here it is in its integrated circuit format, and we can improve on this as well by putting an enable in, but we haven't here. And again, wait for the clock pulse to go low. As the clock pulse goes high, the output changes. And there we are. Now what you can do with D-type flip-flops is you can string a lot of them together like this. And this is 4-bit latch. So, over here we have a data sequencer, and that will put out a binary number, and it will put it out with the most significant bit, i.e. the one on the leftmost, first. So, it'll only do that when the clock pulse goes high. So when the clock pulse goes high, let's say the number it's going to put out is decimal 5, which in binary would be 0101. Clock pulse goes high, it puts out a 0, and this one gets it. And if we imagine that these ones are already 0, we've got 0, 0, 0, 0. The clock pulse goes high, it puts out a 1 here, but the 0 that was in here moves over here. Of course, that means no state change because that was already 0, but never mind. And clock pulse goes high again, it puts out a 0 here, and the 1 that was here moves here, and the 0 that was here moves here. As it keeps going, what it ends up with is moving the 0s and 1s over until we end up with 0, 1, 0, 1. And then at that point there's no more data to come in, and we'll end up with low, high, low, high. And that'll give us the binary equivalent of decimal 5. And what we built there is a memory storage. It's a volatile memory storage, of course, because it needs power, but nevertheless it's a memory storage. And we have a serial in, parallel out shift register. And these are important in electronics and in computer sciences, but in electronics, one of the things we use them for, driving these things, 7-segment LED displays. And you can see what the idea is here. You send a current through a flat bar LED and make it shine, or no current through a flat bar LED and make it shine. And if I make this run now, as everything is off, and there we are, everything that we need is on, and we can make any number we like. So if we get rid of that, and we get rid of that, and that, we've got a number 1. And if we turn everything on except G and the decimal point, so we go like that, like that, like that, like that, we've got a 0, and if we turn G on, which is that one, we've got an 8, and so on and so forth. And by turning LEDs on and turning LEDs off, we have any number we care on the 7-segment LED between 1 and 0. And this is a practical example. And what we have here is this 7-segment LED counting down redly in the manner of one of those old Hollywood films where you've got a ticking time bomb and the hero is running around in his vest, and by the time he gets to 2 he'll defuse the bomb. It's going to be Bruce Willis or Sylvester Stallone or whoever it is doing this time. And these really are the icons of the digital age. They're the first thing anybody thinks about when thinking about digital electronics, principally because in a much smaller version they were used in the very first digital watches. And even today when we use twisted pneumatics rather than the 7-segment LEDs, they still follow the same pattern and look as though they're in 7 segments. I've got a microwave over there with some green ones on that actually does use 7-segment LEDs as the timer. And what they're being driven by is what we've just looked at. And this little black chip here is a 74HC595N. And it's a serial in, parallel out shift register. And what it's doing is it's taking data sequenced by this microcontroller, this Arduino here. And the Arduino puts in binary number, and whatever binary number it gets, the input, it makes high an output where there is a 1 and low an output where there is a 0. On this occasion, because this is a common anode segment, what we do is where there's a high we use to switch off what we don't want, and where there's a low we use to switch on what we do want. And we can change what it does. At the moment it's counting down, so with a little bit of a code change to the Arduino we can make it do other things. So let's make it count up. If we change the way the data is sequenced in the microcontroller, what we can do is we can make it do other things, and as you can see what it's doing now is it's going the opposite way. It's counting upwards, so it goes 0 to 9. And of course, having a number output like that means that we can do all sorts of other things. So let's turn it into an electronic dice. Well, what we have here then is our electronic dice, and we have a little push button here, and pushing the button should shake the dice. There we go, we've got a 6, and we'll go through all the numbers just to make sure. We've got 5, we've got another 5, a 2, yet another 5, 3, and 1, and 4. There we are. Just make sure. Another 3, yep. So that appears to be working. And again, the outputs are being driven according to the input that this shift register is getting, and the input from the shift register is being sequenced by this microcontroller. So let's have a quick look and see how this works. Well, what we can see in front of us is the pinout for the shift register that we're using, and we can see that there are lots of pins marked Q, and whenever you see a Q, that's an output. And the other pins, we have the power supply, which is VCC and ground, and coming down here we have QH bar. Now that's the opposite, and we don't use that at all, we just leave that unconnected. We also have the clear pin, and if we make that low it will reset everything so that all the flip-flops in there read 0. So all we do is leave that high, otherwise we get unwanted data. Going up a bit we have the serial clock, and of course that is the clock input for which we send data. And we have RCLK, and that's actually the latch. Output enable, and on there, on pin 14, we have the actual serial input. And what the data sequencer does is it sends it through 1 bit at a time. Now, you can send through most significant bit first or least significant bit first. And I usually find that it's easier to send through most significant bit first. least significant bit first means it appears at the output as it was at the input. The most significant bit first means it's inverted, and I usually find it easier to work with the inverse. Whichever way you do it, you have to remember that we're working in binary numbers, and if we look at this here, we have an 8-bit binary number here, and there we have a string of zeros and a 1 at the end, and that will be equal to 1 in decimal. And we have a string of zeros and 1 just there, and a 0 there, and that will be equal to 2 in decimal, and again 4, and again 8. Now in your handouts you will be getting the basic introduction to binary. Again here, if we look, what we'll have is we'll have a number here that is equal to 138 and a number here that is equal to 217, and these numbers are important and we'll see why in a moment. So, having had a look at that, we'll have a look at the truth table, and you can see that it's quite a bit more complicated than the truth tables we saw in the combinational logic when we looked at NOT gates. We're not really interested in bar G here. What we're really interested in is the clear, the serial clock and the latch. And we can see that when the clear is in a low state, the shift register is cleared. We really don't want that. We want that kept in a high state at all times. So basically what we'll do, we'll keep pin 10 high all the time. When this is in a don't care state, and this has gone high, and serial clear is of course high, the shift register is clocked, and we're ready to send data. When this has gone high, and this is in a don't care state, and this is of course high, the contents of the shift register are transferred to the output latches. Well, in other words, we get the data. And basically what we do for the microcontroller is we open the latch, we send a clock pulse, we send data, and we close the latch again. And we'll see that in the code when we look in a moment. Now when we looked at 7-segment LEDs, we looked at what was the common cathode. So you lit up through all separate anodes, and you took out through one common cathode to ground. And that's the most easy way round to do it. But here we're using common anode. So what you do is you put power in at the anode, and doing that, all of the segments will light up, providing they've got a resistor at the cathodes. And so what we have to do, these being diodes, if we make the potential at one end equal to the potential of the other, then they'll switch off. So we're going the other way around really. We're using a high output to switch off segments rather than to switch them on. And this is the basic idea of how it's done, and these represent the display digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we want is every bar that we don't want to shine is we need to make high. And here in 0 we don't want bar G, which is the middle bar, to shine, so we make that high. And here in 9 we don't want bar E, which is the bottom left, to shine, so we make that high. Similarly, this is the display number 8, and we want all the segments to shine in there, so we don't bother making any high, and all will shine. And the idea is rather like this. So there's the display 8. We don't send a signal to any of the cathodes here, and all the display segments shine. And there's a display number 0, and what we do is we send a signal to cathode G here. And of course we've got a 5-volt potential coming in at the anode, we've got a 5-volt potential there, so that can't conduct and it doesn't shine. And again, if we want 7, we stop G, F, E and D from shining. We are G, F, G, F, E and D. and if we want 6, we stop B from shining by doing that. And if we look at the code, and this is the code for the upwards counter, what we do is, first of all, we create an array, and it's called shift array, and it's the data we're going to send out to the shift register. We're going to send a series of numbers. So we've got 64, 121, 36 and so on all the way up to 16. If we look here, we've got 0, and that's for when we want to display the number 8. 64, that's for when we want to display the number 0. So, going down, we have 3 pins that are controlling the shift register, and 2 and 3 are going to be our clock and data, and 4 is going to be our enable disable latch. Now in the loop, we have a for next loop, and what we do is we open the latch, and then we send out clock pulse and data most significant bit first, and depending on where t is in its cycle, it'll send out that particular number. So if t is at this point in the cycle, which is 0, 1, 2, 3, 4, if t is equal to 4, it'll send out 25, and so on and so forth. And then, once we've sent out the data, we close the latch and we tell it to wait a second so that we can actually see what it's displaying. Now we have exactly the same array here for the dice, except that we only need 6 numbers. And the reason I put a 0 in there, even though we don't use it on the dice, is that arrays are 0 indexed, and I often find it easier to set position 0 to 0 rather than 1, because then I don't mix position 0 and position 1 up. So I've got 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Okay. Now then, we've done exactly the same down here, but to shake the dice there is a function that we need to look at. So what it does is it picks a random number, and then it just does the same thing. It goes through a for next loop, okay, and it sends out the number in the array. However, when the button is pressed, it does that 100 times very, very quickly. And doing that means it's impossible to load the dice. You can't cheat with this dice at all. There's no way to press the button for a specified amount of time and have it shake a number that you're looking for. The number is completely and utterly random between 1 and 7, and 7 is put there because in the Arduino you always put 1 more than the highest random number you want. It'll never actually pick 7. It'll pick between 1 and 6. And that's the way it's done. We pick the random number, we go through a for next loop, we open the latch, we send out that random number very, very quickly, and then we close the latch. And the shift register will display all those numbers, and if we look at it again, you'll see as we go through that the display flickers on and off, showing all those random numbers before it finally settles on the last one. And here we go then, let's shake the dice, and you'll see that as I keep my finger on the button, or my thumb on the button in this case, it does flicker. And as I said, it's showing all the numbers. Take off, and there we go, and we've got a 2. And that keeps the dice fair, absolutely no way to load it. So that's really the shift register, or at least it's the serial in parallel out shift register. You can get others. You can get the PIPO, parallel in, parallel out, and you can get the PISO, parallel in, serial out, and the one you'll see most often is this one, the serial in, parallel out, shift register. And you always have to put data in with the clock pulse and then reset the latch to get the data to process to do whatever you want. Well, having done that then, we need to look at synchronous circuits because synchronicity is important, and what we're going to do next is we're going to look at timers. Well, there are many ways in which you can make a timer, and if you watch the op-amp video, you'll see that I used at one point an op-amp to make a timer with, and by putting a potentiometer in there, you can make a variable timer. And another way you can do it, if you want very high frequency timers, is to use one of these things. And you may not be able to see that in the camera there, but what it is it's a quartz crystal, and it oscillates at a resonant frequency of 16 megahertz. And you'd use that in microcontrollers and anything really where you want a very high frequency like that. In computers, it's not unusual to find oscillators like this, but much higher frequencies, and in quartz clock you will get one that works at 32,768 Hertz. And the reason for that is 2 to the 15th power, and by using a binary counter you can easily divide it to get a pulse every second, and from there it's very easy to drive gears and motors. If you want high frequencies like that, it's all very well, but it's no good for this game, and what we are going to do is we're going to use this thing. And that is an NE555 integrated circuit. And these things have been around for a great many years. They were one of the first commercially available integrated circuits to hit the market. And we can set them up as astables and monostables. And here we have the two timing circuits built on a breadboard, and at the top here you can see the monostable, which is this part, and at the bottom the astable, which is this part. The two circuits aren't linked together, they are two separate circuits. And we can see that the astable is flashing away, but the monostable is doing nothing at the moment, until I press this button. If I keep my finger on the button, the monostable will keep high. If I take my finger off, it'll go low. That's the job of the monostable. The monostable is so called because it's only happy in one state, and that is when this LED is low. The astable is happy in neither state. It needs to go back to the state it was in previously. And it's all done by these resistors and capacitors. In the case of the monostable, this resistor and this capacitor are forming an RC timing circuit along with a chip. And in the case of the astable, this resistor, and this capacitor are forming a timing circuit along with the chip. So let's have a look at some of the theory and see how it's done. And so before us we see the pin out of the chip and set up as a monostable. And if we consider the insides of here, what we have, I'm going through the pins, we have the VCC, which is positive supply, and ground, which of course goes to the negative rail. And between those we have a series of resistors. There are three linked together, and they are each 5 kilo ohm, which gives the timer its name, the 555. They provide a network, and the network feeds a couple of comparators, and in turn the comparators feed a flip-flop, which feeds an output driver, and there's also a transistor in there for discharging capacitors. And what happens is that the voltage on the comparator is passed to the flip-flop, which is a set reset latch. And depending on what the set reset gets, it'll either put the output driver high or the output driver low. And of course, if the output driver is high, we're getting 200 milliamps of current through there. And we can drive a small LED or something like that, as we saw in the practical circuit on breadboard. If we want to drive anything bigger, it can drive a transistor very, very easily, and we attach that to the output and let the load of the transistor be the object driven. We have pin 2 as well, and pin 2 is the trigger. And when you send the trigger low, that activates the 555 and it will go into a high state. When you send the trigger high, it will go into a low state. Pin 3, of course, is the output, as we've just discussed. And pin 4 is a reset, and the reset can be used to set the output back low. We don't often use it, but when we do, we put a switch in there, and if we don't use it, we have to, as we have done here, send it to the 5-volt supply. Pin 5 is a control voltage, and again, we don't often use that, and here, as is recommended, we put it through a small capacitor to ground. Pin 6 here is the threshold voltage, and this is the actual input to comparator number 2. And it resets the flip-flop when the voltage it sees exceeds 2/3 of the voltage at the supply. And when that happens, the flip-flop goes from the high to the low state, and we get a low at the output. It also connects directly to the RC timing circuit. Pin 7 here is the discharge, and quite simply it's connected directly to the collector of an internal NPN transistor, and it discharges the timing capacitor to ground when the output at pin 3 here goes low. Now, as you remember, on the breadboard we had the monostable circuit, and here it is drawn out in its schematic format. So we've got 1, 2, 3, 4, 5 external components to the chip here, and let's go through them and see what we've got. Now, remember me saying that the control pin is normally put to ground through a 0.01 microfarad capacitor, and you do that if you didn't want any interfering signals there which can cause a false reading at the output. Now, for the short times we've been using, it isn't actually necessary to put that in there, and you can leave control open. If you wanted a more precise thing, then you would do that. R2 is a resistor whose value is not critical, because all it's doing is taking from the 5-volt supply and leading to the switch. So what we're doing is we're making sure the trigger stays high until we close the switch, in which case it will go low and begin the timing on the monostable. These are the two important components, and as we can see, it's R1 and C1. And so R1 and C1 are connected to the discharge and the threshold, and that's what causes the timing. And underneath is the maths. T equals 1.1 R1 C1. Let's scroll over a bit and we can have a look at the A-stable. Now you'll see here what we've done is we've taken the threshold and we've sent the output back to the trigger and to this capacitor, and the timing circuit now consists of 3 components: R1, R2 and C1. And that's because the A-stable has 2 states it can be in. The output can be high or the output can be low, and it's not happy in either state. So whichever state it's in, it wants to return to the other one. Maths underneath gives us T1 equals 0.693 R1 plus R2 times C1. And T2 is 0.693 R2 C1. T1 is the time it will be high, T2 is the time it will be low. Alright, so what we do is we send the charge through there to the capacitor. That will keep the trigger low or high depending on whether it's in a charge or discharge. And of course it can only discharge back through R2. So R1 is missing here. Well, let's have another look at our practical example and then do the maths on it as an example and see what we've got. Now in the pamphlets that accompany this film you will find these worked as practical examples, but while we've got the components spread out on the breadboard in front of us, what we might as well do is saunter through and have a look at the maths in a practical fashion. So we'll start with the A stable, and for the A stable we need to know two things. We need to know T1, which is the time it's on, T2, which is the time it's off. And to get T1 we say 0.693 multiplied by R1 plus R2 multiplied by C1. And the first thing we've got to do, of course, is to add together R1 and R2. And as R1 is a 10k and R2 is 100k, that gives us 110,000. C1 is a 10 microfarad capacitor, but it's no good to us in microfarads, we need it in farads, and of course 10 microfarads is equal to 0.00001 farads. And so if we multiply that 110,000 between those two by 0.0001, the answer we should come up with is 1.1. And we multiply all that by 0.693, and the answer we should come up with is T1 in seconds, which is 0.8. T2, we ignore resistor 1 and we multiply R2 by C1, and again R2 here is 100k and C1, if we multiply by 0.00001, the answer we should come up with is 1. And again, to find T2, we're doing 0.693 R2C1, and we've got 1 for R2C1, so we multiply by 0.693, and the answer we should come up with there is 0.693, and we'll call it 0.7 for roundness sake. Summing the two together gives us the whole duty cycle of this thing, and that should be 1.5 seconds. Well, it looks as though it's slightly under 1.5 seconds, and the problems here are the quality of the components we're using, I think. These are 1% resistors, but the tolerance on this is marked as K. So it could be as much as 10% under, or as much as 10% over. And that'll give us under 1.5 seconds or over 1.5 seconds. Using a K capacitor is done quite often because they're cheap. This one is a slightly more expensive capacitor. It's marked with a J, and that means it's only 5%. However, what we could do, if we really wanted the precision, is we could fit potentiometers in here, and we could adjust the potentiometers to get the precision we needed out of that chip. We don't really need to do it here, it's very nearly 1.5 seconds, and so that'll do. Moving on to the monostable then, it's a little easier because we've only got one resistor and one capacitor. And to get the time that the monostable light is on, what we'll do is we say T equals 1.1 R1 C1. So we multiply R1 and C1 together. R1 is a 47k resistor, so that's 47,000. C1 is again a 10 microfarad capacitor, so 0.00001, and if we multiply those two together, what we should come up with is 0.47. And if we multiply 0.47 by 1.1, what we'll actually get is 0.517. Let's see, it's about half a second. And that does look about right. So there we are then. There's the mathematics. In the case of the monostable, it's very much spot on. In the case of the astable, it's not far off, and it could be the fact that we're using the poor quality capacitor, which might be way out of tolerance. So we're going to complete our video here by coming back round to where we started really, and that's with a flip-flop, and that's what this big 20-pin chip here is. This is an SN74HC574 and it's a D-type flip-flop. And so, we feed it power, positive there, ground there, and like the shift register it has a latch, and we keep this latch low all the time. And by keeping the latch low we can make it transparent data through. This is the astable from our last experiment, and this is the monostable from our last experiment, and what I've done here is I've put the output from the astable to the clock just there of the D-type flip-flop, and I put the output from the monostable to one of the inputs of the D-type flip-flop. There's actually 8 D-type flip-flops on here, and they go straight across like that, so that's input 1, that's output 1, input 2, and so on and so forth. Doesn't matter which one you use, they're all working exactly the same way. Now, this yellow LED is measuring the state of the clock. So, the clock is high when the LED is lit and low when the LED is dark. And what we're going to do is wait for the clock pulse to go low and press the button to trigger the monostable. And you'll see that as I do that, it doesn't matter what the clock is doing, as long as there's a positive signal here from the monostable, this LED shines. And as I let the button go, I'm going to wait for the clock pulse to go low again, and there we are. If the monostable's high, the output from the flip-flop stays high, but if the monostable's low, the output from the flip-flop goes low, but it only does it on the clock pulse. And what I'm going to do now is I'm going to take this 47K resistor out, and I'm going to put a slightly bigger one in, and this is 220K, so let's put him in there. Excuse me a moment, there we are. We should get a slightly bigger time from the monostable, and what I want to watch is the clock pulse as well as the monostable. As it goes high, it goes low. As it goes high, and there we are. So it only goes high or low with the clock pulse. The data changes, but the data on the output from the D-type flip-flop does not change instantly. Let's try a slightly bigger resistor. And this is a 470,000 ohm resistor. So, here we go again. We can clearly see that as the clock ticks away, it doesn't matter until the monostable goes low. And on the rising clock pulse, it goes on, and on the rising clock pulse, it goes off. And that's how the D-type flip-flop works. Now what we could do, if we wanted, is we could put a variable resistor in here, and if we put a much smaller capacitor in, we get a bigger time range. So what we've built here is the basis of an auto off or a sleep function. And there we are. And here's the idea of it shown as a schematic. All we've done is we've taken the monostable in this section here, and we've taken the A-stable in this section here, and we've fed the output of the A-stable to the clock pulse and the output of the monostable to the data, and the monostable will either output a 1 to be high or a 0 to be low, and that's what it'll get in there. The clock pulse, of course, will 1 and 0, the same thing, and on the rising edge of the clock pulse, i.e. when it goes up to 1, the data will be shifted to the output. There is no bar Q on the chip we're using, there's only Q, so that's where it'll shift. And the data will either be 0 or 1, depending on the state of that. And as I said before, if we replace R1 with a variable resistor, somewhere in the region of 1 to 100,000 ohms, and we take C1 down to be a 0.1 microfarad capacitor, we'll get a good time range out of that, and we can set it with variables. If we change the values of R1 and R2, we can make the clock go faster, and we can make the timer much more responsive. So as soon as you press the switch, you'll get the data going through, and as soon as the switch goes low, you'll get the data going through, or at least within milliseconds, rather than the half a second that we had there before. And that's about it for the timer system and for the D-type flip-flop. So to recapitulate what we've done in the course of this video, then we've gone from the basic SR latch and we've looked at flip-flops, and from flip-flops we've gone on to shift registers, and then we looked at timers, and we saw how the timers can be used to synchronize D-type flip-flops. Well, really that's quite enough for one video, and in your handouts that you're getting you will get the schematics for all these circuits, plus a little bit more theory and some mathematics, and I think that's really enough, and we'll conclude the video at this point.